it won't keep you for very long. Clearly we want to listen to Andy's presentation, but it falls to me to introduce him. Andy and I have known each other since the late Cretaceous for you geologists, but for everybody else, since December 1984, when I moved with BP from Aberdeen down to Sunbury, and Andy joined the company then, trundling across in his little white Renault from Nancy, where he'd been a postdoc, and we worked together. We shared a porter cabin, and we worked together and became very good friends. Even in those days, Andy was ploughing, if you like, a particular furrow. He'd worked on oceanic oozes for his research, and then started to work on mudstones. The rest of us were working on sandstones, where the oil was, for goodness sake, not the overburden. Well, it was a couple of years later I found out that in 1990 I was out abroad. Andy had moved from the industrial sector into academia, into Newcastle. That surprised me somewhat, because one of the early stories he told me, having arrived in Britain with this little Renault 5, this white Renault 5, is that it had 2 burst tyres one dark winter's evening whilst driving between Newcastle and the Lake District. I thought he'd never be seen up here again. And speaking of never being seen, we spent a lot of time together. We did a lot of research, but we also went to watch football matches, and particularly at the old Wembley. And the last time I saw Andy, until we managed to persuade him to come here, was at a friendly match between Brazil and England. And at half-time, Andy went to the lavatory, and I didn't see him again until 2012, when we introduced him to come to Durham. Not quite true, of course, but our friendship has stayed throughout. And throughout that time, Andy's knowledge and understanding of these rather mucky, fine-grained rocks has grown and grown, and all of a sudden, from being quite the Cinderella, they may well now be Belle of the Ball. So, Andy, please.
Thank you very much indeed. So thank you both, and welcome to the lecture. Yeah, I think that I think it's an appropriate title, and maybe I have been in the wilderness for 20 odd years, and if you carry on maybe playing the same furrow, you eventually become relevant. So, why Cinderella? So here's a Wikipedia definition of Cinderella, and I think it's quite appropriate. So let's just read that. The word Cinderella has, by analogy, come to mean one whose attributes were unrecognised, or one who unexpectedly achieves recognition or success after a period of obscurity and neglect. The question then is whether that is me, or whether it's Shale, or both. And I think it's a bit of both, to be honest. So today I'm going to be talking about my kind of love affair with Shale. 2 aspects really. I mean, what's been interesting for me in the last 20 years is that probably until 5 years ago, the work that I did had no real interest to anybody, certainly not the media. And with the advent of shale gas, then of course it's become a very sort of trendy subject, and it's been very interesting actually interacting with the media in the last few years. You sort of feel that you have some relevance in the world. So I'm going to be talking about that probably most of the presentation. But at the end, I also want to switch a little bit to sort of CO2. So we have the issue of climate change. Methane, of course, is a greenhouse gas. When we burn it from shale, we produce CO2 and carbon capture and storage, and very relevant to John, who's a professor of carbon capture and storage. Then that needs to be retained. It's stored underground, and what basically retains the CO2 is shale. So it actually covers quite a wide range of important geological issues today. So that's what I'm going to be sort of taking you through. To start with, the broader sort of concept is that, of course, we're a very, very energy-hungry world, especially in in countries like the UK. So what you're seeing here then really is the context to energy. The y-axis there is the millions of people. So we're looking from 1965 up to about the present day. So we've got a hugely increasing population. Not only are those people, more people means more energy, but they're also using more energy per person. So that's kind of like the one-to-one line. You can see we're coming along here. So each individual on the planet as the per capita income increases, we're using more energy. So that's got to come from somewhere. So I mean, that's kind of the overall issue here. And it's not trivial. In the context of shale, then, you know, why is it important today? Well, you know, if you go back 15 years, this stuff didn't really exist. Of course, it was underground, but we couldn't produce it. So obviously, there's a lot of money to be made for a resource of this size, and also we're very, very energy hungry. And don't worry about any of the detailed numbers in here, but the numbers down here is what I want you to feast your eyes on. So in terms of conventional gas, and I'll define that in a few slides, but essentially, for example, it's the gas that we extract from the North Sea, from sandstones. Then in terms of what we might recover, about 190 trillion cubic metres. And the number then is quite similar to what is estimated to be recoverable from the global shale resource. Now, these numbers need to be taken with a pinch of salt, but the point to take away is that they're about the same size. So, you know, it's a very significant resource. So that's kind of the backdrop to why people actually care about these, why companies care about these things. So, first of all, I mean, it's obviously a mixed audience here. So what is shale? Well, it's basically mud. It's mud which has been compacted, it's been buried, it's been heated up and converted into shale. And the point is, and why this is partly about the Cinderella and the wicked step geologists who didn't care about it, there's a hell of a lot of it. So most sedimentary rocks are actually shale. And I'm just going to illustrate that with the Mississippi Delta. So here is the Mississippi Delta. And on the next slide here, I'm going to just take a cross section. So imagine that you're coming out from the Gulf of Mexico, from the Mississippi Delta, down into the deep water, and we're taking a slice down through that delta. And over here then we've got the sediment pile, which is contoured in terms of the amount of sand. Now, of course, conventionally, petroleum companies want to look for the sand in the oil and gas filled sands. And up here in the north, near just the head of the delta, it's mainly sand. Once you come out into the deep water, these red colours, it's less than 10% sand. It's almost entirely mud, or shale as it becomes buried. So these are incredibly important sedimentary rocks. And that's going to be important at the end of the talk when we talk about CO2 storage, in the way that the shales act as cap rocks and don't allow the CO2 to escape if we pump it into storage sites. But of particular interest today then is oil or gas shale. And for the older members of the audience, you may remember these good people. It might even make your heart flutter a little bit, ladies. So here we have Jeremy Irons and Meryl Streep. And why are they on there? Because the French Lieutenant's Woman was at least partly filmed at Lyme Regis. And this is Lyme Regis. This picture here of Meryl, and looks like Jeremy in a clinch, is taken here. And this rock outcrop is just along the coast here. And we take most of our students there each year to look at the much more important things, these rocks. So this is actually there's quite a big oil field on the south coast of England, Witch Farm. The deeper buried equivalent of this is actually the source rock for the Witch Farm oil, and it would be a potential oil shale or gas shale if it was buried to appropriate depth. So a gas shale then, or an oil shale, it's a sedimentary rock. It's a mud. It's a shale, composed of certain mineral types, but critically, it's relatively rich in organic matter. So these are particular conditions on the ocean floor when these rocks were deposited, which allowed organic matter to be preserved. Those rocks are then buried through geological time to temperatures of something like 150 degrees centigrade or higher, depths of something like 5 kilometres. Now, at that depth, it is not going to be commercial to drill wells and frack them for gas shales. And so in situations when, through geological time, those rocks have been uplifted to depths of maybe 1, 2, 3 kilometres, then they have the possibility then of becoming what we would call a gas shale or an oil shale. So that's basically what these rocks actually are. Just a bit of in background in terms of the petroleum side of it. On this diagram, we're looking at temperature going from about sort of surface temperature at the top, 10 degrees centigrade, down to about 160 degrees centigrade. And that organic material, it's algae, it's bacteria. You know, it could be you if you were preserving the geological record. What happens to that solid phase organic material it starts to crack to oil and gas between temperatures of about 100 and 200 degrees centigrade. And the nature of the fluid which is produced with burial becomes increasingly gas rich. So at temperatures between about 100 and 150 we have quite an oil rich phase, and then above about 150 we have a gas rich phase. So that's how petroleum is created in the geological subsurface in what we call sedimentary basins. And you'll see that the nature of the gas actually, the chemistry of the gas actually changes from what we call wet gas. It contains not only methane but ethane and propane, etc. And then at very high temperatures it becomes more and more rich in methane. This is quite an important point for the chemical industry because the chemical industry, for example, uses lots of ethane for ethene and plastics. So they're particularly keen on trying to find or for companies to find gas which contains more of these slightly heavier molecules. In terms of what we burn in our stoves at home, it's mainly methane. So what you find then depends on the temperature at which these rocks have been buried to. So the word unconventional and conventional. So when these rocks, and here's the potential what we call petroleum source rocks, which might become a gas shale, are buried into the subsurface, then most of that petroleum, most of the oil and gas is expelled. And it migrates up to what we call conventional traps. So these would be the sandstones, for example, in the North Sea, from where much of our oil and gas comes from today. A fraction of the petroleum which is generated stays behind. It's trapped in the source rock. And that's then actually what becomes our gas shale. So it's the oil and gas which has been trapped in these rocks. It hasn't been expelled, it hasn't gone to our conventional traps, and now we're going to go in and see what we can find in these rocks. And that has essentially been the gas shale industry over the last 15 years. And it is only an industry which is really 15 years old. I'll show you some slides, but it's absolutely astonishing how quickly this industry has taken off in the US. So production requires fracking. So that's the word that most of you will have heard, and we'll look at it in a little bit more detail. But essentially then we're going to drill vertically to the reservoir, the shale gas reservoir, then horizontally, and then we're going to pump high pressure water and fracture these rocks. And we'll look at that in a little bit more detail. Again, there is history, and it's very interesting going back to the Bible and seeing where some of the old stories come from. So this might be the first instance of somebody fracking a rock. So this is Moses with his staff and bringing water into the desert. And you know what's interesting about that actually in the modern era is that in fact bottled water is more valuable than oil. You will pay more per litre for bottled water than you will do for oil. So maybe we should be fracking for water as well as for oil. There is also actually a very long history of what might be very loosely called fracking. So this is from the 19th century. This says nitroglycerine in here. This is something from a company, the Roberts Torpedo, where essentially this is nitroglycerine put into the bottom of the well, and simply these things were exploded, okay? And in a pretty catastrophic way, frankly. So, you know, environmental legislation in Pennsylvania was not what it is in the UK today. So there is a lot of history of actually breaking rocks apart in the last sort of couple of hundred years. So we shouldn't think about it just as something which has happened recently. And hydraulic fracturing, so going in a more controlled way and breaking up the rocks, that's been fairly common since 1940. If you go down to the south coast in Witch Farm, and if you overlook that area, it's in Poole Harbour. There's some incredibly fancy real estate around there. One of the wells in Witch Farm was fracked about a year ago, and I don't think many people heard about it. You can't see anything. Okay, so you know how these things are reported depends very much on the context. And the critical technology for gas shales, and why it's become a big deal in the last sort of decade or so, is the ability to drill horizontal wells, an incredible technology where you can steer these wells probably within about a metre over a length scale of maybe 2 kilometres, and then pumping in high pressure water and sand to create sufficient permeability for the gas to flow. So it's that technology which has really created this industry over the last 15 years. And they have to be fracked because the basic permeability is the ability of the rock to flow fluid essentially. And shales are basically nanoporous materials. So literally nanoporous. So this is like 1/1,000,000 of a 1/1,000,000 or 1/1,000,000,000 of a metre in size. And so from a geoscience perspective, and I'm a geoscientist, but I'm not going to be talking very much about strictly geoscience tonight. What's really intriguing is here is our horizontal well potentially in here. This is the Kimmeridge Clay Formation for anybody who's a geoscientist, and so we have to decide where we're going to drill that well. Why do we put it in a particular place? And there's the scale, so that's about 10 metres. So we might imagine that a gas molecule somehow has to get from, say, here to this wellbore in order to make the industry some money. And that's a very interesting geological engineering issue. As we go down scale, so this is like a little sort of a thin section of a rock down in a microscope, about 1 centimetre, and then just down here in the G.J. Russell facility in physics, there's some beautiful microscopes, electron microscopes, which allow you to see the size of the pores in this material. And this is a bit of organic material in a section of one of these rocks. This is 10 to the minus 7 metres, a tenth of a micron. Okay, so that's less than, that's 1/10,000,000th of a metre, and these are the little holes in which that gas sits. And so it's a very non-intuitive and interesting problem about how the hell you get gas from these small pores, maybe 10 or 20 or 30 metres away from that well into the well bore. And that's a very, that's a really intriguing geological issue, and it's a very intriguing engineering issue. And not for tonight. In general, then, how do the fracking operations actually work? This is the site at which Quadrilla drilled its pre-Saul well a few years ago, the one which is famous because there's an earthquake which was associated with it. It's about the size of two football pitches. This is during the drilling operation. And essentially what you're doing is putting a large amount of water. So here we have some water tanks. You're adding a small amount of certain chemicals, but particularly what they've called here a frack concentrated polymer. It's usually something like guar. You put it in foodstuffs, it's not a big deal. It's just to make the water a little bit more slippery, basically, so it's easy to inject. There are some chemical additives. There's some biocide in low concentrations, but generally not that big a deal. I do not understand why the industry has been so quiet, at least in America, about what chemicals it adds, because the vast majority of these are actually very benign, and they don't do themselves a great service by not telling us what they're putting in the injection fluids. And the other thing particularly important is proppant. So they go in, we're fracturing this rock, you're basically pumping in the water until the rock cracks, and then you're trying to keep those fractures open by injecting some sand. It's usually sand is the cheapest proppant, so we have sand silos in here as well. So that's basically how it works, and it maybe takes a few months to actually drill one of those wells. The other thing to understand is that the drilling is actually pretty clever now. So this is a slide from Corporation Chesapeake in the US, and so they're drilling what they call multilateral and multi-stage fracks. So what that means is then from a single pad here, then they can drill multiple wells, maybe 6 from each one. You can see them going out laterally for along there, here and here and here. So for a relatively small surface footprint, then you can interact with quite a large amount of rock, and that's obviously important from a sort of environmental perspective. So you actually get a lot of energy for a relatively small surface footprint in this technology, and they do it in sort of multiple stages along there as well. So that's kind of the way it happens. A pad of about a football pitch, which will then probably drain an area of maybe a couple of square kilometres, something like that. So these laterals go out maybe 1, maybe 2 kilometres from the pad. So it's very clever engineering. Now let's look at the US. So essentially all the action in the world is from the US, and what we have to do here in the UK is to understand and learn from the US and determine what will work for us here. What are the issues? Can we do things better? Do we have to do things better environmentally, maybe, in terms of producing more per well? These are the issues. Now, there's a variety of reasons why this industry has taken off so much in the US. It's partly just the US mentality. It's partly about geology, which is in many cases fairly straightforward in the US. And it's partly because there's an unbelievable amount of shale there. So each of those pink areas is an area of the US where there is the potential to produce shale gas. So these are humongous areas. So the most famous from the granddaddy, that's probably not the right word actually, it's only been 20 years, so it's a bit too young to be a grandfather. But the original one is the Barnett Shale here in Texas, and that's that pink area. So if I put the area of the UK as a square on top of the Barnett, it would be about the same size as the Barnett. So it's like having a gas shale which is basically the same size as the UK, and that's just one of the ones that they can produce from. So huge areas and therefore huge potential for gas. The other thing, of course, now from the US is that there's a lot of data. They have drilled a lot of wells. If they were going to recover all of the gas that they think they have, they would need something like 800,000 wells. And you know, they're not going to get there, but they are drilling a lot of wells per year. Now, thousands of wells per year are being drilled in the US. The other important statistic from this graph is how much gas you can produce per well, because that tells you how many wells you have to drill in order to produce a certain resource. And so we're going to take these numbers and think about it in the UK context. And so the amount of gas which seems to be producible from one of these wells, this is in billion cubic feet, the numbers don't matter too much, but you know, typically between, well, most commonly around 1 billion cubic feet for each well that's drilled. And if you do it really well and you're lucky, maybe up to 6. And clearly, the more efficiently the companies can drill the wells and extract the gas, the fewer wells you have to drill. And that's going to be an important challenge, I think, for the industry in the future. Point about these slides then is that we're going to be looking at the UK situation and seeing what's the implications of these data for us. The second thing then, I want to take you to the Eagleford Shale, which has been a really kind of hot area in the last 5 years. So this is right down in southwest Texas. It's right on the Rio Grande on the Mexican border, right in here. I was lucky enough to go on a field trip there a few years ago. This is an outcrop. This could not happen in the UK. This is an outcrop which is leased by BP. So you can only go to it if you work for BP or if you're one of their guests. And it's kind of the middle of nowhere. And you think, well, how do they police it? How can you stop people going there? Thing is that when the rancher comes along in his little, you know, Scooby-Doo thing with a gun rack on the back, that's how you know that they patrol it. So you know, this is fairly wild country, and it's quite heterogeneous for you geologists. But what I want to show you on the next slide is just what's happened there in the last 5 years, because the amount of wells which have been drilled, the activity there has been absolutely astonishing. And so we're basically down here, and there's what they call the play, or the area where they do the drilling. It's kind of in a line from sort of in this direction through just down in there. So the next slide then is a nighttime shot from a satellite image in southwest Texas. And here we have Houston. So I think that's the 4th biggest city in the US. Here we have Austin and San Antonio. So this is about, I don't know, about 3 or 4 million, about 1 million each of Austin and San Antonio. And that's the Eagleford at night. That's what it looks like on the ground. So there's just an incredible amount of activity. You know, this is constant drilling through sort of day and night. And so since 2008, they've drilled 7,000 wells in that area, and they've got approval for 5,500 more. So these are absolutely astonishingly large numbers. And we'll come back and think about that number in the context of CO2 capture at the end of the talk, in terms of how many wells would we need, for example, for CO2, and can we do it? Okay, so it's quite useful to think, you know, you can drill a lot of wells per time if there's an incentive to do it. So it's an incredible change in that area, and clearly it's easier to do it in the sort of relative middle of nowhere in Texas compared to even the desolate northeast of England. The other thing, of course, is that energy is politics and it's money, and again, it's incredible how the US energy economy has changed in the last few years. So what we're looking at here actually is what we call petroleum products, but just think about it as oil and gas. And this goes back from just post-war to about the present day. And you can see that all the time since post-war until about 2010, 2009, then the US was a net importer of petroleum, you know, oil and gas. This is shale gas, basically. Shale gas and shale oil that's changed this, and it's just recently become a net exporter. So that's an incredible change, and that, you know, that's a political issue. You've got to think about, you know, would we have had Iraq and things if this was the case? You know, it's hard to know, but you know, energy and politics are very closely aligned. The other thing which exercises the public's mind and politicians' mind is also the gas price. It is true, so this is just data up to 2010, this is today, so for whatever the units are there, the US pay about $3.6 for that, is it 1,000 BTU I think it is, or something, million BTU, and we pay about $11.5. So this is an incredible difference. And again, it's because of there's basically a gas glut in the US. Now, our politicians would like to persuade us that that would happen in the UK. It won't. It won't. The US is a very unique market in that until very recently, they have had no way of exporting gas. You have to liquefy gas to export it, and all their terminals are basically set up to bring in liquefied gas rather than export it. But that is changing right now. So I think this price is going to increase. I don't think our price is going to decrease very much. We're in a much more global market, and you know the demand for gas is increasing. So I don't think these numbers will change very much. I think that this number probably will start to increase. But you know, these are big differences. I think I heard, admittedly, a petroleum person said that he thought that the shale gas industry had contributed something like $500 billion to the US in the last, whatever it was, 10 years. These are substantial numbers. And it's probably one of the reasons why the US has come out of recession, you know, more quickly than Europe. So it's been a big, you know, it's been a big deal in the US. The other thing, of course, in the US is they have data. They drill a lot of wells, they produce a lot of gas. And here is one of the problems with shale gas, in that the wells do not produce significantly for long periods of time. Conventional wells flow more oil and gas over a longer period of time. So again, the details absolutely don't matter here, but the data from a variety of US shale gas plays, and you can see that typically in 3 years you lose about 84% or a number, 80% of the production. And of course that's a real commercial issue. You have to keep on drilling to keep on producing the gas. So that's one of the reasons why you have to drill so many wells. Now, can we change these curves? I suspect not. Can we go in and refracture and produce more? Yes, we can do, but this is a real issue. And so you can see after about 3 years, these things are becoming kind of almost like sub-horizontal. So small amounts of gas going longer term into the future. So that's an important issue in terms of longer term production. Okay. So what about the UK then? Let's switch from the UK from the US to the UK. Well, I said it even in that one area, the Eagleford, they drilled, was it 7,000 wells in the last 5 years? How many wells have we got in total? Well, it's about 3. I'm not, you know, I kind of forgotten actually whether it's like 1, 2 or 3, but it's a very, very small number. You know, so I don't know, you know, is that pathetic? It might be. We've got no production, and that's true in Europe in total. That means that we have very, very little data. On the other hand, the UK has a pretty worrying energy situation. You know, we're kind of on the edge. Nuclear's falling off the cliff. We're not becoming more energy hungry, but you know, the North Sea's in decline. Nuclear is being shut down. So we have problems here in the UK. And so I think this is the key issue as we think about this. We're very energy hungry. We like our lifestyles, guys. You know, we want to fly around the world and we like our cars. So we want to burn a lot of energy, but we're very concerned also about the environmental things. We don't want things to happen in our own backyard and all the rest of it. So there's a real sort of tension there in the sort of political, socio-economic context, which of course makes it a very interesting area. Okay, so where does gas fit in the UK? And actually, you know, we are very dependent on gas, petroleum in general. So this is a diagram then going from 1970. Today, and then projections to 2030. So this is the total energy then in the UK. So you can see that coal is you know, very, very small indeed. Petroleum or oil is hugely significant still. gas is very significant, bioenergy and waste is tiny, and this is electricity. Okay, that's the total power. And you can see it's not, this is from DEC, the government. It's not really suggests it's going to be changing that much through to 2030. Now, you look at the electric specifically, then I was hoping to show you how we were getting electricity this minute, but I couldn't get an internet connection. So this is from yesterday. So this is the electric bit of it. So remembering that, okay, so here's our gas, here's our oil, and here's our electric. But of course, lots of the electric is coming from gas. So that's the total that we were burning at 1 o'clock yesterday. Or, not burning, or we were using this much electric. So that much from gas, that much from coal and nuclear, and then there's bits and bobs of a little bit of wind. It wasn't a particularly windy day yesterday, and we're importing a bunch from France. So in addition to the power for oil and gas, also quite a lot of our electric comes from petroleum. You'll also see that it's CO2. So you can see then for gas, it's producing much less CO2 per unit of carbon, if you want, than coal. That's well known. One of the reasons why climate-wise we'd like to move more away from coal and to gas. So so overall, and you can see that gas, and particularly oil plus gas, incredibly important in this country. It's something like 70-75% of our energy is currently coming from oil and gas. The other side of it then is the supply gap that's occurring in this country, and I find this really scary. So you can see then in 2004 we were basically self-sufficient in gas. We now import something like 30% of our gas, remembering how important it is as a fuel for us. And by 2020, we're probably going to be importing about 80% of our gas. Now, that's not necessarily a problem. We've got a small country to the northeast, Norway, where nobody really lives there. They have a lot of gas, and they're very benign, and they sell it to us. So I'm sure a jolly good price. And the second imports are from Qatar. Possibly a less stable place. And just in the last few weeks with what's happening in Ukraine, this is a very sort of dynamic situation. We don't get much gas from Russia in this country, but you can see that politics is playing a big role as well. So that's actually quite scary. We're very dependent on gas, and we're having to import more and more of our gas. And that's part of the backdrop to the shale gas. What could it do for us in this country? So let's think about that then. Let's just take a couple of slides, think about the US, and think, what might it mean for our currently favoured shale? Many of you may have heard of the Bowland shale in northern England. This is its kind of, it's what we call its subcrop, so it exists everywhere below the surface in this purple line here. This is a little cross-section, geological cross-sections, lots of faults in there. You can see, and this is kind of like the great black shale hope for the UK. And again, let's not concern ourselves with all the detailed numbers in there. But if we take the numbers from DEC, and we think we can recover maybe 15% of it, that tells us that there's about 2 billion cubic feet for each square kilometre of Bowland shale in that area. What does that mean in terms of what we need in terms of pads? Well, if we recover about 1 billion cubic feet per well, that means we need a pad with about 6 wells and those laterals drilled out about every 2 square kilometres. That's a lot of pads. That's a lot of pads. It's not impossible, but that's a lot of pads. So there's one of the issues then. It's a lot of lorries, it's a lot of pads to make a difference. The other slide then from the US experience for the Bowland shale. So DEC produced a very nice report last year about how much gas might be in the Bowland shale. I mean, to be honest, we don't know. There's no real data, so we're kind of making it up. But their best estimate was about 260 trillion cubic feet. And these are the numbers that go onto the BBC. They are big numbers. People get very, very excited by them. The question then is how much you can recover, and what is what's the surface footprint of that recovery. So 15% recovery is what people think, what the scientists think. That's about 40 trillion cubic feet. That's about 13 years of UK gas use. So that's quite nice, you know, it's 13 years of gas use is nice, but it's not like a massive game changer. And that's if you produce the whole thing. That's not going to happen. It's just not going to happen geologically, and it's not going to happen for societal reasons as well. And so again, if you were going to produce all of that gas, and I think, you know, this is probably a non-starter, but if you were, then you need up to about 30,000 wells, about 5,000 pads. So that's a lot of surface footprints. You know, a lot of people aren't going to like that. So these are the issues. So I don't think that's going to happen. What if we did 25%? Well, 25% would give us about 3 years gas. So they're the kind of numbers I think which are out there. So this is not a game changer in the UK. It's relevant. It brings money to the treasury. It creates jobs. We use steel and concrete, but it's not a game changer in terms of energy. And also, we have to accept that we're going to have to drill a lot of wells onshore. And we haven't done that in the UK really ever. So here are the numbers, and Richard Davis, I think somewhere in the room has sort of dug out these numbers, so thanks Richard for that. So we've drilled on average about 20 onshore wells per year, and these are the offshore data. We drill about 100 UK offshore wells per year, compared to what we would need here, which are in the thousands. So it's a massive step up in terms of drilling from what's happened before. So they're the issues that we have to face. Okay, next bit of the talk then. We're doing on time. Okay, next bit of the talk then. What about the issues? I want to skip through these actually quite quickly because colleagues like Richard Davies and Simon and John have done this a great job on this in the last couple of years and have published a lot about it. So transport disruption. What I mean by this is a lot of lorries on site. I'm not going to talk about that, but it's an issue. The geological issues then, how much water do we use? People are worried about that. They're worried about contaminating aquifers. They're worried about seismicity. Not worried, but probably should be, about leakage through boreholes. And then we've got the big one, the climate change at the end. Okay, so water use. Well, you know, we live in a pretty wet place. And it is true that you use a lot of water to fracture these wells. But this is data again from the US. In terms of the percentage of total water use on shale gas, it's a very small, it's an incremental amount more. So not for me something to worry about. Any water which is produced back from the wells is often saline. That has to be treated. It has to be disposed of according to sets of rules, which we have in place through the Environment Agency. So for me, not that important. Fracking. Are we going to contaminate our aquifers? There's a lot of data from the US. They've drilled thousands of wells. There are seismic ways of monitoring where the fractures go. And what you're looking at here then, this is basically the depth of the shale, and these lines then represent the distance to which there has been some sort of seismic noise, some microseismic noise, looking at the distribution of the fractures. And the basic point here is they go nowhere near these aquifers. So it's absolutely not something that companies do not want to fracture into aquifers. They want all the energy to be in the reservoir, and there's no real data which suggests that that is likely. So as long as we are producing at a sensible depth, then contamination of aquifers is very unlikely, at least through fracking. What about seismicity, surface felt seismicity? I mean, again, these are data then. This is the, you may have heard of the Richter scale, the sort of energy scale of earthquakes. Essentially, until you get to a magnitude of around 2, you will absolutely not feel this at the surface. Even at 2, it's maybe like a car or a lorry going past outside. It's not that big a deal. These are data, -2, -1. These are data from fracking in the Barnett Shale. Interestingly, one of the very few felt earthquakes was the first time we drilled a well in the UK. Now that is sort of, so is that telling something about the UK, or is it telling something about the company shouldn't have drilled there? You know, that's something which we have to take care of. But these are very rare earthquakes indeed, and even magnitude 2. You know, it's not something to worry about. Talk to somebody from New Zealand. They're just not on the radar. You know, they don't. It's just not important. I think I'll skip that one. Okay, the thing which maybe we do need to be a little understanding of, and this is the longer term duty of care, is about the boreholes. And again, Richard and colleagues have dug out a lot of data for this. And so this is like a shale gas production site when it's kind of in good nick. They're pretty small. You know, once the drilling rigs have gone, there's very little to see. It's not that big a deal in terms of its footprint. But of course, through time, they maybe become abandoned, they start rusting, they get plugged with cement, but cement corrodes. You know, we've bored holes into the ground. This is where the leakage is most likely to be. Steel and cement do corrode. And there's data then from Pennsylvania and Alberta, where there's thousands of historical wells, which suggesting that, you know, a small fraction, but a significant fraction of these wells do actually leak. And we can then decide whether we actually care, or to the extent to which we care about that. But this is maybe the biggest issue. So it's the long-term duty of care. You know, those wells then, they are running for maybe, I don't know, we don't know now, but maybe 10, 20 years. You know, just sort of flatlining, just in terms of low production. So what happens when we sort of shut those in? Who looks after them? It's the same with the mines, the historical mines around here. Who owns them when the companies go away? What's the duty of care? So that's an important kind of legal issue. It's an important historical issue. So this is Pennsylvania, you know, 7,000. I mean, these are all the abandoned and orphan wells in one area of Pennsylvania. You know, they could look like this. Now, of course, this is from way back when. We wouldn't want to do anything like this, but it's an illustration of the issue. So it's the long-term duty of care. It's partly about monitoring. You know, if we're worried about getting methane into our water supplies, we need to, you know, leaking from casings, then we need to know what the baseline is, and then we can test through time. So it's all, you know, it's all feasible. It takes time. It takes money. And the longer term duty of care, perhaps, and this is the sort of the final group of slides, is the climate issue. So when we burn our methane or ethane or our coal or whatever, of course we produce CO2. And I'm sure you're all aware then of the issues surrounding climate change. And I don't think there are many, certainly geoscientists and you know, meteo people who don't believe that there is a strong relationship between the CO2 that we are injecting into the atmosphere and climate change. And it's been very interesting in the last, few months with the Intergovernment Panel on Climate Change, who for the first time in their report started to talk about sort of mitigation and engineering issues, whereas before they've only just talked about the issue of climate change. So this is out there, and you know, whether we believe in 2 degree, 3 degree, 4 degree increase in temperature, it is an issue, and there are many people, many economists who believe we need to do something now. It would be cheaper to do something now rather than let this go for another sort of 50 or 60 years. You know, I have to say that I'm kind of sceptical, but let's kind of give it a go. So in the context of CCS, and John, who introduced me, is a much bigger expert on this than me. But the essence of it then is we capture the CO2 at a power plant, for example, and we're going to pump it underground. It could be an existing oil field, a depleted oil or gas field. It could be into a deep aquifer. And the link to this talk, partly because of just the whole thing's about energy, but the link to this talk in terms of shale is that the cap rocks are these low permeability rocks, which basically will retain this carbon dioxide, hopefully through geological time. I think we are told that we need to retain it on the order of 2,000 years, which of course is a blink of a geological eyelid. It's nothing. It's nothing. So it's the properties of shales, the fact that they are, the fact we have to go and frack them to get the gas out tells you that naturally without those fractures, they're very low permeability, they will not let much gas go through them through geological time, you know, unless we do something wrong, unless we actually sort of create conduits through the shales as a result of injecting the CO2, and that's the issue. So what I'm going to show you then is a few slides of some of the work that we've done and some work that's also been done by Statoil and the British Geological Survey in terms of CCS. And what do we know about these shales basically as a way of retaining the CO2 in the subsurface. So first of all, a few numbers. We generate about 30 gigatons of fossil fuel CO2 per year. In 2015, there will be supposedly 16 sites, sort of demonstration sites to capture CO2, and that's going to be about 0.036 of megatons of CO2 per year. So I think this should be gigatons in here. It's gigatons. I changed them all except that one, yeah, gigatons. So that's about 0.1% of what we put up into the atmosphere. So it's zilch, basically. The IEA is suggesting that by 2020 that should be 0.3. So it's upscaling by a factor of 10, and they hope for 8 gigatons by 2050, which might be 27% of what we produce. So this is a massive upscaling in terms of our CO2 capture. And when you think that, I guess we started, or Statoil started a project, I'll show you some slides of this, in a place called Sleipner in the Norwegian sector of the North Sea in 1996, 20 years ago, right? So in 20 years, we've gone from 1 to about 16. We need a hell of a lot more. We need thousands. We need about 3,800. That's a big number. But remember, in the Eagleford, they drilled 7,000 wells between 2008 and 2013. We don't need to drill wells here. We've got to take the CO2 and pump it down. So it's not impossible. But it has to have a big change in our thinking, our attitude to the cost of energy for that to happen, or the value of CO2, if you like. So that's going to be the big issue. It's not impossible, but it's a big change, and it will put some money on our energy bills. And of course, we want to do it safely. And even if we do that, then this is a graph. Then this is the annual emissions of fossil fuel CO2 from 2000. You see, it's been increasing, not decreasing last decade. It's been increasing. It's about 30 gigatons per year now. This then is the number which the modelers suggest that we need to get to in order to sort of stabilise the temperature of the planet to less than 2 degrees centigrade beyond what it is today. So that's a change from 30 to about 10. With those CO2 numbers, with that massive increase in CO2 capture and storage, that would go to this red line here. So we would still need to reduce our fossil fuel burning by about a factor of 2, almost, rather than a factor of 3. And that's with a massive increase in CO2. All right, so we still have a long way to go if we're going to keep the climate down below the 2 degrees centigrade, even with CCS. Of course, that's not to say we shouldn't be doing CCS. It's part of the solution amongst several other solutions. So what do we know about leakage? That's what I think a lot of the population cares about. What do we know about leakage? Well, we don't know very much about CO2 because we've not captured and stored very much. But geologically, of course, all those conventional sites which contain oil and gas, they've held the oil and gas for millions of years. So they are telling us something about the nature of those shales and their ability to retain any fluid, including CO2. Now, I know from my good students' work is that actually almost everything leaks on geological timescales from hydrocarbon reservoirs. So I've just picked out some data here. What you are looking at, and again, please don't worry about the details here, but we have an oil and gas accumulation in some sandstones down here. And there we have our cap rock, our seal, our cap rock, our shale cap rock, from about that point there up into the so-called overburden. And we're looking here at, it's called the wetness of the gas. And basically, once we're away from the y-axis here, this gas composition tells us that the gas has been leaking up from this sandstone. It's just about the nature of the composition of the gas. Please don't worry about the details. And so, and we've looked at something like 50 or 60 of these reservoirs, and you always find this, small concentrations of hydrocarbon gas leaking up through the overburden. And in this case, it's gone, about 600 metres into the overburden. But it's done that over probably 20 or 30 million years. Not a problem for CO2. For CO2, we're talking about retaining for maybe 2,000 years. That's what our masters tell us, 2,000 years. So, so this bit of leakage is actually not a problem. In fact, I would argue it's probably quite a good thing because it gives a bit more storage space. That's a hard thing to get across to the public. Like, leakage is bad. It's all relative. This tells us that leakage is kind of okay as long as it's slow and controlled, and that's what our shales are doing for us. We also know about seepage. So here we are, coming back to the Bible. I think Moses was a geologist. So the burning bush, almost certainly a gas seep. You know, that's almost certainly was a gas seep. Azerbaijan, this is a mud volcano. It's got gas that's coming out of it. The gas has caught fire. So you know, not a huge distance from the kind of biblical lands. Here's one in New York State. Very pretty one. This has been burning for all of recorded history, so at least hundreds of years. It's very prettily behind a waterfall here. And interestingly, this is actually coming from shales, actually. So this down below, these are kind of like sort of gas shale type things. So we're very familiar with seepage, and you know, we don't really care about it. The tourists come here. It's okay. So what about CO2? Well, we know quite a lot about CO2 leakage. Again, it's about risk. It's about risk. So it says here, pericolo di morte. So I guess that's danger of death. And this is a little area where this is a natural CO2 seep, of which there are hundreds and hundreds in Italy. All these little round circles are places where you get natural CO2 leakage. And yeah, I'm not sure that I would want to come and actually stand on here, but you can see that it's very, very localized. The issue is very localized. And there's some amazing quote here. This is actually from a journalist, but so the Proceedings of the National Academy of Sciences, that's a serious journal. I mean, that's supposed to be the truth. And so however they did it, and I can't get into the details, you know, and so you know, you can walk up to this. It's not you know, you're allowed to. You're a tourist. You can do what you like. So 1 in 280 million is apparently the risk of death from CO2 poisoning here, compared to eating a peanut butter sandwich, which is 1 in 3,300. So you know, it's about risk perception. So is a bit of leakage a problem? You know, I'm not sure it is. I think there are bigger issues out there. You know, I think that 300 people dying in the Turkish mining accident yesterday, energy is more important than a bit of CO2 leakage. So let's get some sensible risk into this. And so finally then, what do we know about CO2 storage? And the only place I think where we've really got good data for, and you know, Statoil, the Norwegian oil company, have driven this, is from a place called Sleipner, and they have been injecting CO2 into, not the oil reservoir, it's into an aquifer. You've got Sierra sand since about 1996, and it's about 15 megatons now. It's been which is, you know, a tiny amount. We do 30 gigatons a year, so 3 orders of magnitude more come out from the globe. This is a very important but small site. But it tells us a little bit about the chances of leakage. The rock into which it's being introduced is down here. It's a sandstone. This is a seismic section. It's about a kilometre below the surface. It is, so for you geologists out there, this is basically, these are shales in here, and these are sands. This might be a field analogue where we have sand, shale, sand, shale. So that's the kind of rock into which it's being injected. And we're interested really in whether it's been leaking out of the structure. And what Statoil have been doing is a very clever thing with seismic data. So seismic is basically shooting sound waves into the ground. And a rock which contains water responds differently to a sound wave compared to a rock which contains CO2. So you can kind of monitor where you've got water and CO2. So if you inject CO2, you can kind of see where it is through time. Very clever. It's also very expensive, which is why we can't do this on most of the sites that might be used. So here it is. It's in the horizontal drilling. It's being injected into the base of this sand, and then we've got some seismic monitoring to tell us where it's gone. And again, let's not worry whether you're geophysicists in the room, but these lines here represent essentially geological strata, and Statoil went in and they shot seismic in 1994 and then through to 2006. And where the colours change is an indication of where the CO2 is. And it's being injected here at the bottom. It is making its way up through the reservoir, and interestingly through some thin shales within the reservoir, which is intriguing and maybe disconcerting. But there is no evidence that the CO2 is leaking beyond what we call the cap rock. Okay, so this gives us quite a confidence, I think, that in Sleipner then we're able to hold that CO2 in place. The shales are able to hold the CO2 in place for, well, at least for this on this time scale. And to make it look prettier, then that's where the CO2 is. So we have, this is our sand section here. The CO2 is being injected in here, and it's basically being pondered below these shales. It is somehow managing to poke its way up through the shales, and not quite sure how that's happening, and I don't think Statoil are either. That's probably a topic for a glass of wine. So the CO2 is there, but critically there is no evidence that the CO2 is leaking up through the cap rock. So the shale cap rock is doing its job in maintaining the CO2 down here. So this gives us some confidence, but it's one site, and the cost of doing 3D seismic is phenomenally expensive. So if you're going to do 3,800 sites, there is no way we can monitor it using seismic. We have to think about other monitoring techniques. And John will chat to you about that afterwards if you want. So where are we likely to leak? Well, again, it's the boreholes. You know, if you put a hole in your roof, that's kind of where it's going to leak, right? So the rain's going to come down here, not through the. So this is kind of like slate. It's like shale, and here's the borehole. This is where the fluid goes, and back to the the gas shell thing. You know, you abandon these things, you put casing in, but there's probably, that's the most likely place where you're going to leak. Just local leak spots. Now, is that bad news? Yeah, it is. Is it serious? It depends how much CO2. Not necessarily. You know, it's a risk issue. So the rocks, the shales look pretty good. Where we puncture holes in the shale, we may need to be a bit more concerned about it. So that's basically it. Some concluding thoughts. There was this fabulous quote a few weeks ago from, so Ineos is a gigantic chemical company, so it's like a multi-billion pound chemical company, and he wrote this letter to Jose Manuel Barroso, the president of the EU or something like that, anyway, an important person, and it's like, great, it's not looking good for Europe. Mixed metaphors, isn't it great? We are rabbits caught in the headlights, we've got our trousers down. So I don't quite know what he meant, but he basically says, we need to get our act together. Are we going to do it or aren't we going to do it? You know, they are actually, they are renting tankers to bring ethane across to Europe from America to drive their chemical plants. Okay, and we're kind of sitting around thinking, oh shit, what are we going to do? So, we're going to make some decisions really. In terms of the UK, it might be a nice little bonus if we want to go for it, but it's not going to be a game changer. I don't think we have enough, and there are probably too many issues in terms of how many pads we can get permission for. Do we need more science and technology? I think we do. A lot of wells in the US still don't work very well, and wouldn't it be nice to go from 1 billion to say 3 billion, in which case we don't need to drill so many wells. But if we want to do it now, we can do it. We know enough about the geoscience and the risk to go for it. In terms of climate change then, shale gas, going from coal to gas, plus CCS, it gives us a bit of breathing space, but that's all it does. We still have to either change our lifestyles or fundamentally increase renewable energy. So this is good, but it's not the ultimate answer. And with that, folks, I have to go.